Start.
Yes? We can start. Yes. So in this last part, that will be 28 minutes, we will discuss different topics like the instruction of LLMs. So the idea is that pre-training is important, but it is important that we teach the LLMs to do specific tasks. For instance, we need to instruct them, for instance, with instructions like write, generate, describe, explain, etc. And then this is the main idea that basically it was introduced by this very impactful paper that instructed GPT, and it is the predecessor of ChatGPT on which OpenAI was based. So the idea is that we need to fine-tune to align a large language model with human instruction and feedback. And if this task is done, then very small models like 1.3 billion Instruct GPT are giving better responses than the huge 175 billion model GPT-3. What is the life cycle of instruction? So we have three phases. One phase is that we need to collect human instruction data. For instance, we have human labelers that they give us pairs of instructions and answers with some examples, and we fine-tune the LLM with this data set via supervised fine-tuning, as we mentioned. At the second step, we need to train what we call a reward model that essentially we have human labelers that among different answers to a specific question, for instance, we have explained reinforcement learning to a 6-year-old child, and we have 4 different answers. We have a human labeler that, let's say, puts an order, a decreasing order of preference, and these preferences made by humans are training a reward model. So these 2 models are used then at the third step, which is the optimization of the LLM based on the human feedback via a PPO policy, proximal PPO policy that is essentially initialized by the supervised one, then it generates an output, and then the reward model gives the reward that is given back to the PPO model, and this cycle fine-tunes the model to a better performance. So these next slides, perhaps I will kind of go through them fast because they are explaining what I just said. The interesting thing here is to mention that there are different types of instructions. For instance, we have generation tasks, query answering task, brainstorming, rewriting, summarization, open and closed query and answers, extraction, classification. And these are types of, for instance, brainstorming is list 5 ideas on how to regain enthusiasm for one's career. On the math side, the reward model essentially is training. So YW is the optimal answer, and YL is another answer. So YWN is better than YL, and we are training the model on this difference as a loss function for all pairs of answers. And then we have the proximal policy optimization, which is the reward model that is trained on 3 different, let's say, 3 different elements on a pie of which is the learned reinforcement policy, the PI-SFT, which is the supervised model, D-pretrain is the pretrained distribution, and we see here this is a complex objective function that basically takes into account the distance, the reward between the input and the produced output. It takes into account with the weight beta, the KL divergence between the optimal, between the reward policy and the supervised fine-tuning. So these two models, ideally they should be aligned, and also takes into account the pre-trained model probabilistic distribution. Then we have the concept of prompting. So what is prompting? Prompting is how to, let's say, ask queries to the model, and by the way that we are asking queries, we lead the LLM give us good answers or even improve its quality. So we have different ways of prompting. There is the zero shot, the few shot, and the chain of thought variants that we can compose them. So the zero shot learning contains essentially only the query, and so the LLM must produce an output. And zero shot prompting by itself doesn't perform very well. There is the few shot prompting, where you ask the query, for instance, this is a movie review sentiment classifier, and then you give 3 reviews, 1 positive, three examples of reviews, 1 positive, 1 neutral, and 1 negative. And then you give a new review like, I really enjoyed this movie, and then you are asking whether this is positive, negative, or neutral. So this is the concept behind the few shot learning. And then we have the chain of thought, where we need to somehow provide a kind of explanation or an algorithm behind the answer, and this seems to be improving dramatically the performance, but only in the case of very large models. So the chain of thought, it is an emergent ability of model at scale, and it is significant for models above 100 billion parameters. So here we have some examples of few shot chain of thought. For instance, we have the standard prompting, where we ask the query and then we give the answer, and then asking another query usually results in a bad answer. But if we provide an explanation, for instance, Roger started with 5 balls, then 2 cans of 3 tennis balls, each 6 tennis balls, then we give the addition. So this is like explaining why the answer is 11. Then the LLM, in a similar question, it will give not only an explanation and a chain of thought, but also a correct answer. So this is the concept of chain of thought. And then there is the combination between zero shot and chain of thought, which is essentially that we are, let's say, here, we simply add, let's think step by step. So only by adding this sentence after a zero shot question, which means that there has not been any previous experience to the LLM for that, but only adding, let's think step by step, it makes the LLM explain and give better answers. And again, I stress that these are properties of very large language models in the areas of above 100 billion parameters. And there are very interesting, let's say, papers on that. So only this little difference in the prompting, let's think step by step, is doing the zero shot let's say, prompting to improve from 17.7 in the multi-arithmetic dataset to 78%. Only adding this sentence makes the model improve dramatically its performance. And then if we add some samples, it improves further. And this is a kind of research that shows that zero shot with only adding this sentence chain of thought improves dramatically the performance of the models. Then we move to the topic of parameter efficient fine-tuning. What is the idea behind that? So when we do fine-tuning, what does it mean? It means that we have a model, 100 billion parameters, that we want this LLM to learn to do a new task. This means that we need to expose it to a new data set that is teaching to the model this new task, for instance, 3-digit multiplication. But the result will be that if we do this in a brute force manner, the model will be as big as the previous one, and we need to store the fine-tuned model that corresponds to this new task, and for every new task, so we have a huge space needed for storing these models. So the result is that full fine-tuning results in the need to store a full copy of the model for each task. For this reason, the research community and the industrial community came up with what we call parameter efficient fine-tuning, that essentially uses the previous model as is. It doesn't modify it, so it freezes the model. And there is what we call augmentation by smaller models with much fewer parameters, and combining the previous frozen model with the small fine-tuned model gives a better results. The main methods there is the adapter, the prefix, and the LoRa. So let's see what is the adapter fine-tuning. The basic idea is that we have this transformer architecture where the layers are very big. As you remember, we have billions of parameters inside here, and we inject what we call adapter modules. This is the architecture of an adapter module, which is a small encoder-decoder. So we have the original dimension here. We decode it into a smaller dimension. We decode again into a larger dimension. The dimensions of the adapter are much less than the ones in the decoder. So what we do is that we train only the adapters, and the rest of the model is fixed. Only doing that, we see here, for instance, they compare. They have a BERT large model where they do fine-tuning on the entire model that achieves an 80.4% accuracy in this task. And by using this solution, the adapters, with only 3.6% of the original parameters, they achieve a performance which is only 0.4% less. So with 3.6 parameters training, we achieve almost the same performance as the full fine-tuning. So this is the adapter. Another way of doing PEFT is the prefix tuning. So what we do is that we have the input, and we prepend, concatenate before the input some additional few parameters, few tokens that are adapted to the specific task. For instance, we have these prefix tokens for the table-to-text task, for summarization, for translation. So for each task, instead of fine-tuning the whole model, we train only these prefix tokens that are prepending the data. So this comes with very interesting results. For instance, we see that with only 0.1 parameters with prefix tuning, it outperforms or achieves comparable performance with fully fine-tuned models. Okay? So these are very interesting results. And the last one, and in my opinion the most interesting one, is the LoRa that capitalizes on dimensionality reduction, in the sense that we have the pre-trained model that has the fully fledged, let's say, model, which is huge. Then what we do is that we freeze this, and in parallel, we train a model that has the in and out dimensions that we need, for instance, the input and the first layer, but the intermediate dimension is small. So this means that the weights that are being trained is the product of A and B, which is 2 times D times R, which is much smaller than D square, which is this one, if R is much smaller than D, and this R dimension can be even as low as 1 or 2. So this means that we have very low number of parameters. So essentially what we do is that we have this frozen model and we add this AB or BA multiplication of trainable parameters, where the size of this is orders of magnitude less than the previous one. So this is called low-rank approximation. And for instance, GPT-3 with LoRa achieves very competitive, let's say, performance with only 0.1% of trainable parameters. Finally, we have, let's say, 10 more minutes. So I will speed up. Anyway, the topics now are a bit less technical. So in order to train LLMs, we need data. And data, as we have heard a lot of times, data are precious. And let's see what is about data and pre-trained models. So we have several different collections of open source data that contain collection, cleaning, filtering, deduplication, which is important. It is important that we don't have multiple copies of the same data because this destroys somehow. We also need to make sure that we have privacy, let's say, privacy maintained. So we have all these different data that you can access. It is very interesting data sets of trillions of tokens. Then it is not enough to have only pre-training data, but we need also instruction tuning data, which is very expensive to get because they are arising from human labeling, which is expensive and hard to get. So we have these 3 data sets of multi-language and English prompts. For Bloom is an important provider of such instruction data. Lion, 43 million instructions, and Databricks, 15K instructions that corresponds to 5,000 employees that were helping with this. We also need open reinforcement learning related data, alignment data. Here we have 3 data sets that corresponds to thousands of people volunteering for this. So human evaluation is always very important still. And then it comes to the concept of open LLMs. It is important, as we mentioned, to have open resources. So there is the Bloom, the French model that was trained in the last, let's say, some few years ago. And it is given in different versions ranging from 500 million to 176 billion parameters. The instruction tuned version as well is free. We have the Mosaic ML versions that are very interesting. We have the TII Falcon in different versions, and we have other models, including the recent JAIS model that Embizu AI is involved in and focuses on the Arabic language, which is a very interesting topic, especially in the context that we are today. And the last slides about the evaluation of LLMs. It is known that ChatGPT broke the Turing test, so we don't know anymore if we have a human answering our questions or a machine. So for this reason, we need additional challenges. For this reason, there is the famous Hugging Face LLM leaderboard, where we have the different, many different LLMs and their performance in different data challenges. For instance, ARC, HELAS WAG, MMLU, etc. Just very brief, I would say, very brief description. So we have the ARC dataset, that is a dataset of multiple choice question answering. It is split in two partitions, the easy and the challenging ones. Here we have the split into different categories ranging between analogy, explanation, algebraic, logic, etc. So these are the type of questions, multiple choice, and we have, for instance, between 4 and 9 different choices, and the correct one is given. Here are more categories. We have also HELA-SWAG and MML U1 and 2 that are essentially 57 tasks, a massive set, a massive test consisting of multiple choice questions like this one, and some of them, they are far from trivial, okay? And there are 16,000 questions in total. This is an interesting slide, one of the concluding ones, which is the transparency of the different models. So we see that models by Meta are probably the most transparent ones for different aspects like the data, the computation, the methods that they have been used, the risk, the mitigations, and all that. The red means closed source, the blue means white, it means open source. We see different types of attitudes with regards to giving access or not to the different aspects of LLMs by different companies. And finally, some challenges. Multimodality, in my opinion, it is an interesting next future. For instance, there is this new model, FUYU, that takes as input an image. It breaks down the image into patches, so it is training a decoder together with the caption, and we can train together in a decoder directly image and text, trying to combine multiple modalities. Of course, this goes beyond. We can have sounds, we can have graphs, etc. Some final thoughts, somehow personal opinions. So it seems that LLMs know everything that has ever existed in digital form. So it is beyond that, it is knowledge that it is beyond any single human. The size of the models, as we mentioned, they present this nonlinear phenomena, which means that they may be capable of capacities that we have not even imagined. Already the best art is based on AI. You probably remember this 2022 digital art competition in the United States that was won by somebody that was prompting an AI. Many people ask, can LLMs create new concepts? In my opinion, and in many other people's opinion, it is definitely a yes. Here is an example that it is myself asking Bing, for instance, if it can create a new concept in the area of graph operators learning. And in my opinion, it makes total sense, this one. The question is, what is happening in the future? The future is very interesting in the sense that we have opened the Pandora's box that brings, of course, positive but also very high risks that we need to mitigate. And in our final slide, I would like to, in 1 minute, show a little bit what we do in our group in Ecole Polytechnique, and also in collaboration with the group in MBizu AI. So we are working on LLMs, and at the same time on graph machine learning, and we maintain an interesting set of language resources. It is not LLMs, it is LMs, I would say, but it covers French, Greek, Arabic language. It was the first open source Arabic, let's say, large model. It is called Arabart. And recently we moved to multimodality, where we combine protein graphs with text predicting the function of a protein. And in this case, I conclude the talk. I need to express my gratitude to my dear colleagues that we have gone through so many years together. Thank you very much.
Interest of time, we will not let you ask questions, so because Michalis will participate to the round table this afternoon, and so we will have much more time to discuss, and also he's there, so he's not shy, so you can ask him questions. So the next speaker is Eric Xing. So Eric Xing is president of Mohammed bin Zayed University of AI. It's the first university in the world which is completely dedicated to artificial intelligence. So me and Michalis, we are adjunct professors there. So it's an excellent destination for AI. It's already in the top, I would say 20 now in computer science department in the world. So I think the impact of Mohammed bin Zayed University and BZY is already extremely large. Mohammed bin Zayed is also university which is supporting with G42 one of the biggest large language model in the world, which is JAIS, which is in particular with a special interest in Arabic language, as was mentioned by Michalis. Eric Xing is also a professor at Carnegie Mellon University in the US. He's very, very well known. He's a famous professor, a lot of publications. So all of us willing to have his Google Scholar Index, which is really stellar. He's also someone involved in many startups and more than startups, like so he has companies already. So he's extremely, very, very proud to have Eric today with us. It's another Eric. So I'll leave you the floor.